Hi friends, welcome to today's video on gradient descent. A gradient descent is a very important concept that is asked very frequently in interviews, and it is essential that you understand this particular concept so that your understanding of machine learning algorithms becomes better. So let's go ahead and understand this concept and see how it is used and what are some of its advantages and disadvantages. But before we go to gradient descent, let's first understand some terms associated with it. The first term is called minimization. So, minimization is a problem where we are trying to find the minimum value that a particular variable can take. Let's say, for example, here we have a cyclist whose work is to find the fastest route from A to B. Now there are multiple routes. There is one that is in green color, there is one in red, and there is one in blue. And his work is to find the fastest route. And assuming that he is traveling at the same speed, irrespective of which path he is taking, the shortest route will be the fastest route. And the shortest route between A and B is the straight line that connects them, right? We have learned this in school. So this kind of a problem where he's trying to find the shortest path between A and B, the shortest distance, that is a minimization problem because we are trying to minimize the distance out of all the different distances that are available to him. And if we have the exact opposite problem, let's say we want to find what is the longest path from A and B. We want the cyclist to lose weight, and so we want to make him take the longest path instead of the shortest path. So if that's our problem, then that's a maximization problem because out of all the routes available from A to B, we want to find the one that has the maximum length. And in this case, that will be the green path, right? So this is what is maximization and minimization. And in business, these are very commonly used terms because frequently we hear things like how to maximize our revenue or how to minimize our loss or how to maximize our customer satisfaction or how to minimize the defects in some product that we are manufacturing, right? And this process of finding the maximum or the minimum is also called as optimization because we are trying to find the optimal solution based on the resources that we have available, right? So even if we are trying to solve the same problem, let's say I'm trying to solve the problem about maximizing customer satisfaction, but the optimal solution for that may be very different between two companies. Company A can have a very different solution and company B can have a very different solution even if they are targeting the same problem because it is based on the resources that are very specific to them, right? And as a data scientist, there may be so many problems that are given to you where you have to find the optimal solution. So it becomes essential that you learn some algorithms and some ways to be able to achieve that. So now that we understood a little bit about maximization, minimization, and optimization, let's come to gradient descent. So the word gradient means slope, or if we want to talk in the terms of mathematics, it means the partial derivative of a function with respect to the input parameters. Now, if you don't know partial derivative, that is okay. Just remember that gradient is representing slope and descent means decreasing or going down. So combining these two together, what gradient descent means is decreasing the slope. It is an optimization algorithm which tries to minimize the value that a function returns. It does so by iteratively moving in the direction of decreasing value of the function till it reaches the minimum value. So few things to remember here. First of all, it's an optimization algorithm. Secondly, it tries to minimize the value of a function. And third, it does so iteratively, right? It keeps on repeating the process again and again, and it always moves in the direction of decreasing value of the function because it is trying to find the minimum value, right? For example, in case of linear regression, one tries to reduce the sum of squared residuals to find the best fitted model, right? So this is a minimization problem. We are trying to find the sum of squared residuals, but the minimum value for it, right? So um, uh, if we apply gradient descent to that problem, our function in that case will be the sum of squared residuals, and then iteratively gradient descent will keep on moving in the direction of decreasing sum of squared residuals till it finds the one which has the minimum value, and that model would be considered as the most accurate representation of the input data to the function, right? The function that gradient descent algorithm tries to minimize is also called the cost function. Now you need to remember that it's not a constant function. This function changes based on the problem. Like for linear regression, it could be the sum of these squared residuals. That is the function we are trying to minimize. But in case of some other problem, it could be a completely different function. What is constant? The algorithm is constant, but the function that we are minimizing, that keeps on changing based on what is the business problem that you are trying to solve. Now let's say we have a function called y equals to fx, right? So y is our output, our dependent variable, let's say in the language of linear regression, and x uh, are all the different input parameters that we give into our function to calculate the value y. Now fx could be any function, right? If it is linear regression, it is the sum of squared residuals, or it could be any function. But let's just assume for the sake of simplicity that y equals to fx is our cost function, and I want to minimize y. So from all the values that y can take, I want to know what is the minimum value, right? If I put different values for x, y will throw different values. So I want to find which is the minimum value that y can take. And I want to know, why do I want to know that? Because I want to know what is the value of x when y is minimum. For example, when the number of defects in my product is minimum, what are the different input parameters which are causing it. Let's say I find that the number of defects is minimum when the number of quality engineers who do a quality check on my product is 10, right? So it then helps me to take a decision that, okay, I need to have 10 quality engineers always available. Then only the quality check process will go fine, and my number of defects will stay at a minimum. I cannot go below 10. I can go 11, but I cannot go below 10, right? It helps me to take those kind of decisions so that my number of defects, the y that I want to minimize, stays at its minimum value. So that's what I want to know. I want to know x, because then I can control it. I can make sure that it is never compromised, right? So let's say my cost function, so in this case, is y equals to fx. And like I said, we want to iteratively move, like gradient descent will iteratively calculate one value after another value of y till it finds the minimum value. So how does it do that? It does that by help of this particular function. So y new is the next value of y that it's going to calculate. And it will calculate that by subtracting this value from y old. So let's say this is my first value of y that I calculated. My next value of y in my next iteration, when I will calculate it, I will actually subtract something from it. And then I will get my new value of y. And I will keep on doing this. So in the next iteration, this y new will become y old, and I will again subtract this particular amount from my y old to find the next y new, right? And what is this? This is the partial derivative of my input. I could not find the shape of partial derivative d, so I have just used the regular d. But that's what it is the partial derivative of x, fx with respect to y, and this alpha is my learning rate. learning rate is like how fast I'm moving from one point to another. That's what it determines, and it's a constant value that does not change. And when you are building your model, and if you have chosen the gradient descent algorithm, based on whatever tool or language you're using, you have to kind of manually give the learning rate, and then it will take that as input and uh, keep on calculating or keep on minimizing the value of y. So yeah, so that's how iteratively it will keep on calculating the partial derivative and multiplying the learning rate to it and subtracting it from the value of y to try and find the minimum value for y. Okay, so now here I have couple of plots to show you how the gradient descent algorithm works based on that formula that we saw in previous slide. So let's say that this is my function, that y equals to fx, that function is this. And this is my minimum point, right? And then I want to find this point, and I start at some random point here, right, which is my y old. And then this red line represents the slope of that line, and this is a positive slope, right? And now if I take and input that slope value here, multiply it with alpha and subtract it from y old, so now my y new will actually be a smaller value from y old, right? Because I'm subtracting a positive slope and my learning rate is anyways positive. So I'm subtracting a positive value from my y old, so my y new will be a smaller value. So I will move in this direction, right? So this direction is the direction of decreasing y, right? So now my y new will be maybe somewhere around here. So I'm moving closer towards my minimum point, right? So in the same way, I will have one more iteration, and I will keep moving in this direction till I reach this point. On the other hand, if I have this function and but I calculate my y old somewhere here, it's a negative slope. So what will happen in that case? So a negative and a negative slope will become positive, and my y old will actually then move in the other direction. Here it was moving towards the left, right? Because we are subtracting something, it was moving towards the left, but here we will add something, so it will move on the other side, which is once again closer towards the minimum point. So I'll move from here to maybe somewhere around here, and then we'll keep on moving till I reach this point, right? So this, if you see, is a convex function, isn't it? It only has one minimum point, right, which lies at the bottom of the convex shape. So if my function is a convex function, then I only have one minimum point, and I can easily, I mean, not me, gradient descent algorithm can find it pretty easily by following this iterative process that I just described, right? It will keep on calculating y, and if it is a positive slope, it will subtract that slope multiplied by learning rate. If it is a negative slope, it will add it, and then it will keep on moving in the direction of the minimum point till it finds it. But what if my function is not convex, right? That's possible. What if my function looks something like this, right? It doesn't have one convex shape. It is really a very complex kind of a function. Now, if this is my cyclist and he now starts moving in this direction slowly, and he reaches this point, based on the gradient descent algorithm, he will think that this point is actually the minimum point, because as soon as he moves in this direction, he's moving upwards. So he may assume that this is the minimum point because he has no view of what is going in the surrounding and the minimum value of this function is actually here, isn't it? And in the same way, he may think that this is maybe my maximum point, but the maximum point is actually somewhere around here, but he has no view to it, right? So the red colors, the lines in the red colors, they are representing the something called the global minima and the global maxima, because globally, all throughout this function, this is my minimum and this is my maximum. But if I look at locally, only if I only locally look at this part of the function, then this is my minimum and this is my maximum. And what happens is, with the problem with a gradient descent algorithm is that while it is pretty good in finding local maxima and local minima, it may mess up if my local maxima and minima are different from my global maxima and minima. And the reason for that is the way it works, right? Once it finds this point here, it may think is that its work is over and the algorithm may just converge and stop looking for this minimum, because for it to move from here to here, it will think that okay, my slope is now increasing, so maybe I'm going in the wrong direction and this is my minimum, right? It has no view to see what's going on here, and that is a big problem with gradient descent algorithm. It works well with convex function, but for more complex shapes it may not find the global minimum. And the other problem is, if too small of a learning rate can take very long to converge with many input parameters, making performance an issue, right? If my learning rate is very small, that means in every iteration I'm decreasing or increasing my y very little, right? So then if I have a lot of input parameters and every time I'm decreasing y very little, then it may take a really really long time, right? For the function to converge to the minimum value, right? On the other hand, if my learning rate is very high, then I may completely miss my minimum point. I may jump from one maximum to another maximum, right? Because I'm taking like really, really large steps and I'm subtracting or adding really large values to my y to calculate the new y. So I may completely end up missing the value that I'm looking for, right? So these are some problems. And the other problem is that it has a dependency on initialization, right? We and Like I said before, learning rate is manually decided, so you have to do a lot of trial and error maybe to find out what is the right learning rate. And in the same way, when it comes to initialization, you have to initialize your starting point with gradient descent, and that may also create problems based on your initialization, how the algorithm then proceeds forward, right? So these are some problems with gradient descent. And there are some other uh, algorithms and some other ways that one can deal with these problems. You can go ahead and search for that and look for that and see how can you counteract these problems that are with gradient descent. But it's a very very important concept. I hope I was able to explain it to you. If you still have doubt, then always you can put some comments and ask me about it. I will try to try to make you understand. And once again, thank you so much for watching. Look forward to the next video on regression on Sunday. And if you have not already, then please subscribe to our YouTube channel. We are going to be bringing you so much data science stuff. So please subscribe and also follow our Facebook page to know all the updates about what videos are going to come. And share it with your friends. Invite your friends also to subscribe to this channel. And thank you so much once again. Talk to you again on Sunday.